So now we're going to talk about variability. And we saw variability before when we were looking at this data right here, that it's not only the average or the mean, like if these are suppliers, like it's not only how long on average does it take them to deliver a part to us once we've placed the order. Just get my talker going. It's 8 a.m. But you know, it's not only about like what is the average. So we're looking at descriptive statistics here. We're looking at numeric measures to describe our statistics. And one of those numeric measures is the average or the mean. And so the average or the mean for each of these data sets with all of this data in it, the average or the mean for this data set and for this data set, it's 10 for both of them. So on average, when we place an order with John's Parts Company or Robert's Parts Company, on average it takes 10 days for that part to get to our warehouse. But that's not the only thing we should think about. So mean average is a measure of central tendency. On average, you know, where's the center with all of those arrows hitting around the target? Where's the center around which all of those arrows are clustered? It's not only the average or the mean that we should think about, we should also think about the dispersion or the variability of the data. So we've already touched on this, but the dispersion and the variability here is like, you know, the mean is 10, but the data is like either 2 on one side or 2 on the other side. So it goes from 10 to 8 or from 10 to 12. So the variability is like 2 on each side of the mean. It's not that much. But over here, the variability goes from like 2 to 30. So the mean is 10, and sometimes they're 8 days earlier, and sometimes they're 20 days later. So there's much more variability or much more dispersion there. And when it comes to looking at data to make decisions, we not only want to know a descriptive statistic like the mean or the average, we also want to know a descriptive statistic like how dispersed is the data? How much does the data vary? How much does it vary? So what are some of the ways that we might be able to figure out what are some numeric measures? What are some numeric measures that we could use to better describe our statistics, our data set with all of our data? What are some numeric measures we could do to describe that variability or that dispersion? It's a good question. So I think I need to get a glass of water. So one of the ways we could describe the variability or the dispersion is with range, right? We could say, hey, well, what's the difference between the smallest and the largest data in the data set? And so here the range is 4. The difference between 12 and 8, 12 minus 8 is 4. So by having range as a measure of dispersion, the dispersion of our data, or a measure of how much our data varies, the variability of our data, range helps us. It's a numeric measure, a descriptive statistic, which helps us gain insight into what is the variability or what is the dispersion of our data. That's super important, right? Or over here, we could see the range, the difference between the largest piece of data and the smallest piece of data is 28. So with both of these figures right here, we are empowered. We are empowered, people. We're empowered to make a better decision. We could say on average, each of these suppliers take 10 days to deliver their order, but the dispersion, the variability of the data, we can see that with the range, and the range, the number of days, like, you know, the high between the high and the low, about how many days it took them to deliver the order. The range for John's Part Company is 4, and the range for Robert's Parts Company is 28. So just based upon these two descriptive statistics, right, these two numeric measures, we can make a more informed decision. And we could say, you know what, let's stick with John. He's more consistent. Robert over here, don't know what's going on, right? The guy's a little bit all over the place. So based with those things, a measure of central tendency, like the average or the mean, and then also a measure of dispersion or variability, like the range, we can make a better decision. Here's my question for you. What other numeric measures could we come up with to capture dispersion or variability? So think about that for a second. I'm going to get a glass of water. When I come back, I'm going to answer that for you. I'll be right back. All right, I got a glass of water. I feel like I kind of just need to take a breath. Sometimes when I'm a little bit like, gotta go quick, doing something called 4-7-8 breathing. So 4-7-8 breathing is this thing that Andrew Weil talks about. Andrew Weil is Western and Eastern. We'll look him up. 4-7-8 breathing. Please describe. And thank you. And then we'll look up Andrew Weil. So here's 4-7-8 breathing. And I'll just give you a little introduction to it right here. Right? So ChatGPT is going a little bit slower. ChatGPT is just waking up this morning also. So and then I'll demonstrate for you. I'll demonstrate it while that's coming out. So you inhale for 4. You hold for 7. And then you exhale for 8. Or a little longer. Inhale. Hold. Exhale. Inhale. Hold. Exhale. So that's also very similar to box breathing. Please describe box breathing and how first responders use this. So we'll let that describe there. But first responders use box breathing. And when they get into really tense situations, it's like inhale, hold, exhale, inhale, hold, exhale, inhale, hold, exhale, inhale, hold, exhale. So inhale, hold, exhale, pause. Okay, I left out the pause. So inhale, hold, exhale, pause. So they do box breathing, and so that helps them stay chill in super tense situations. And then please provide a short paragraph telling me about Dr. Andrew Weil. Dr. Andrew Weil, and he's a really fascinating guy, wrote some great books, but he really studied both Western medicine and also Eastern medicine. And so he has these great insights into, like, you know, what's great about Western medicine and what's also great about Eastern medicine. Eastern medicine being like more homeopathic stuff and nature and herbs and things like that. So he has some really cool books, and he started a program, a medical program in Arizona or New Mexico or something, where you could go to med school and you could learn both Western and Eastern medical practices. Super cool. So already after doing a little box breathing, that chilled me out. And so I feel a little bit more grounded and a little bit less rushed, and I'm ready to start talking about statistics without feeling that pressure in me, like I got to get it all done because I got to be out of here in like 45 minutes to get to class on time. And so it's all a rush. And I really love not only teaching the curriculum that's in the textbook, what I'm supposed to teach in each course, but also just taking a moment to share something which I think is insightful and helpful. It's been beneficial in my life because every single one of us as humans, we hit those moments where we need to just calm down, slow down, become more grounded, and chill out. And so these techniques can help us do that and help us do better at work, help us do better at home, in relationships. You get into tense situations, a tense conversation comes up, there's some kind of a difference, somebody's grumpy, you could take a couple of breaths. And this has actually been like super studied and to be super effective. And I could even feel it and hear it in myself after just doing it 3 times. So that's good stuff to learn. Now, back to statistics, ladies and gentlemen. So what would be another way that we could measure variability or dispersion? Well, really what we're looking at here is if this is the measure of central tendency, if this is the mean, we want to see if the data is really close to the mean, like this, or if data is all over the place, like there's some data way out here and there's some data way out here. Is the data dispersed, widely dispersed around the mean, this measure of central tendency, or is the data narrowly grouped around the mean, right? So we could measure that dispersion. And so one of the ways we could measure that dispersion is I'm going to insert a couple of rows here. So I'm going to insert a column to the right. I'm going to insert one more column to the right. And one of the ways we can measure that dispersion is we could say how far away is this data point from the mean. And so to do that formula here, I could put an equal sign And I could say this data point here, how far away from the mean is it? And this is 2 less than the mean. And then I could add to my little formula up here. I know that's pretty small, but I could add to that dollar signs in front of both the column reference, the B, and also in front of the row reference, the 2. And so when I do that, you can see the formula there. It's going to be B2 right here minus B8, so the mean. And putting that formula in there with the dollar signs, now when I copy this and bring this down, it's always going to reference B8. So that's an absolute reference when you put the dollar signs in front of the column reference, the B, and in front of the 8, the row reference, right? That's an absolute reference. So as I copy this down, it's absolutely always going to reference B8 for that part of the formula. And this other reference, B2, as I copy this down, that's a relative reference. So relative to where this formula is, it's going to take the number to the left, and it's going to subtract this number here in B8. And as I move this down, relative to where this is, it's going to take the number to the left, and it's going to subtract B8. Relative to where this is, take the number to the left and subtract B8. So that's how you do a relative reference and an absolute reference. I probably already showed you that, but it's good to know, and repetition is the mother of mastery, and practice leads to progress. So good to see stuff again, just reinforces it in the mind. So here we could see that the dispersion, the variability around the mean for John is like, for this piece of data, it was -2. It was 2 less than the mean. For this piece of data, it was +2. It was 2 more than the mean. 2 less than the mean. 2 more than the mean. No difference between this piece of data and the mean. And you know, it's interesting that all this adds up to 0. So I'm no statistician. When I got my master's degree, I actually emphasized finance. I definitely took statistics, but like I did not get a PhD in statistics. So I don't know if this is always the case, but every single time I've ever done this, it's been the case. So I kind of think that that makes sense, that the mean, the average, when you take each data point and you subtract, you know, from the data point the mean, that all these are going to add up to 0, because that's the measure of central tendency. And then you've got stuff on both sides equally, almost like it's a fulcrum, right? You got the same amount on one side as you have on the other side to keep it balanced. So these have always for me added up to 0, which is kind of interesting. So this is like another way that we could do variability or dispersion around the mean. And but if you add all these up, it gives you 0. So what else could you do? Well, you might consider taking the absolute value. Consider taking the absolute value of each of these. And if you take the absolute value of -2, you get 2. If you take the absolute value of 2, you get 2. -2, take the absolute value of that, you get 2. So if you take the absolute value and then you add all of those up, you get 8. And so that would be like some statistic, just hypothetically thinking about this logically. That could be some statistic that we use to figure out like how much dispersion there is. So we've got the range, but we could also create this new numeric measure, just thinking about this logically, where we're subtracting how far from each data point it is from the mean, and then we take the absolute value of each one and we add them up, and we might call this the mean average deviation. And in fact, I think that is actually a statistical thing, and I stumbled upon this, maybe I remembered it from the classes I took way back in grad school, but please tell me about the mean absolute deviation, or whatever that's called. I'm not sure that's the name. Not sure that's the name, right? And this isn't in the textbook. Yeah, you're right. You're on the right track. The term you're looking for in the mean absolute deviation, it's the measure of the average distance between each data point in a set and the mean of that set. In other words, it tells you how spread out the data points are from the mean. Here's how you calculate the MAD. And then here, let's say we have the data set this, and it gives us the mean of this. And for each data point, we subtract it from the mean. We get all that. We take the absolute value of each of those. And then we add all those up, and we divide by the number of data points, and we get 2. So that's the part I didn't include there, is divide by the number of data points. But we were like on the right track in figuring that out. And so that's one way we could do it. We could take the mean. Another way we could do it is we could square all of this stuff. So if we square -2, because I want to get rid of the negatives so this doesn't add up to 0. So if we square -2, we get 4. If we square this, we get 4. If we square that, we get 4. If we square that, we get 0. And then if we add all of that up, 4, 8, 12, 16, if we add all that up, we get 16. So I'm just going to put 16 here because that's like my total column. See, it says total right there. And I'm going to just insert one row below there to kind of drop it away from the mean, or those two. And I'm going to delete this row right there. Just kind of bring those together. And so here is my total of those. I got 16. And what else might we be able to do is we have this formula right here where we sum up, we get the difference between each data point and the mean, we square it, we add them up, and then we divide by n-1. N-1 for some reason when we're dealing with a sample. When we're dealing with a population, so here's this notation page. I got to go back to my 4-7-8 breathing for a second. Getting keyed up again, I don't know why. Statistics, it's complicated terrain, territory to navigate. So in my brain, what's happening is kind of like I want to say it correctly, and I don't know what happens, but I feel pressure to try to get it right. So in here, here's the notation. That's kind of funny, right? That's called mindfulness, being mindful and aware of your own self-experience. So when you're mindful and aware of your own self-experience, it helps you better, choose the experience that you're delivering and regulate and manage your experience so you can optimally perform. Because if you don't know what's going on with you inside yourself, you don't know yourself, you're just, you're unconscious, right? You're unconscious. And who knows, you're just going to act however you act, and you're not going to have choice in the matter. Mindfulness gives us choice in the matter. Taking a breath. So here's the notation we use for populations and for samples, and that big N for a population, the little n for a sample, and when we're calculating the mean or the average, we use mu for a population mean, we use x bar for the sample mean, and for the variance, we use, for a sample, s squared, and for the population, we use sigma squared, that's sigma. And that's kind of fun because right now, all the kids are saying sigma, and I actually do not know what that means. Let's take a risk. I have noticed that a lot of young kids, like in late elementary school and even in junior high and high school, they're saying sigma and sigma. What does that mean? What does that mean? That mean in this context. Sorry, we're having a few tangents this morning. I know too many of them. Refers to popular meme and trend that has emerged in recent years, particularly among young people. The term sigma is derived from the Greek letter sigma and is often used in internet culture to describe a certain personality type, archetype, typically in contrast to the more well-known alpha and beta types. A sigma male has gained popularity online, is used to describe a man who's independent, self-reliant, and doesn't conform to traditional social hierarchies like alpha males, who are seen as leaders, or beta males, who are followers. The sigma male is often portrayed as a lone wolf who goes his own way, doesn't seek social validation, is seen as mysterious and aloof. The term sigma, exaggerated masculinity, interesting. All right, well, that's cool. Learn something every day. All right, so what are we doing? We want to see this one here. So for variance, right, we get the difference between each data point and the mean, and then we square it, and then we add up all the squares, and we divide by n-1. This is little n. I drew it like big N, but that should be little n, and n-1. And so and then that gives us s squared. So that's the notation we use for a sample, and then here's the notation we use for a population. We're getting the same result, but here the data is a sample data. Here the data is a census, all of the data in a population, but it's doing the exact same thing. And so to do that, we have 16. So I'm going to come down here and I'm going to do variance. And you know what? I'm going to do it like this. I'm going to do insert row below, insert row below, insert one column left, insert row above. Go below, man. Insert row below. There we go. Because then that gives me a green row. It gives me all the formatting. It's all bold. So my variance here is going to be equal to this amount, all divided by n, and n is going to be 1, 2, 3, 4, 5. 5 minus 1, and do that. And now we've got 4. Hey, my variance is 4. That's kind of cool. And let's compare this variance with Robert, okay? And then we'll call it good on variance. So I'm going to insert a column to the right and insert a column to the right. And if I do here the difference between this data point minus the mean, and I'm going to press F4 on my keyboard to put those absolute references there. I'm going to copy that, and then I'm just going to copy this one down. Boom, 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 boom. So 30 minus 50 is 20, 5 minus 50 is 45, 10 minus 50 is 40, 2 minus 50 is 48, and 3 minus, ooh, but I did that wrong. I don't want to do it against 50. I want to do it against the mean. So let's do this again. So I need to change this data point from E7 to E9. So I'm just going to come up here. I'll do it right here because it's bigger. And manually say, and manually I'm going to say, statistics is a little bit, you know, there's a lot of little I's you got to dot and T's you've got to cross. So there's the difference between this data point and the mean. The difference between this data point and the mean, 5 minus 10 is negative 10. Difference between this data point and the mean is 0. Difference between 2 minus 10 is negative 8. 3 minus 10 is negative 7. So now that we have that, we could square these. So I could say this is equal to that amount times that amount. That's how you do the square, is you multiply something by itself. I'm going to press enter and then control C and then highlight all that. Hold down shift and use your arrow keys and you could select cells. Holding down shift, I'm pressing my up and down arrow keys, and now control V to paste that formula over that range. And there's all my data, and then I'm going to add all this up, and I'll go over here and get my sum formula and drag over all that to put in that range, G2 through G6, and then I'm going to press enter, and I got 538, and then I'm going to come down here and say this is equal to that amount divided by n minus 1, 1, 2, 3, 4, there's 5 there, so 5 minus 1 is 4, and it's 134.5. So we could see here that, like with versus John's versus Robert's, that we have a variance of 4 and we have a variance of 134.5. So this variance number is much larger than that variance number. There's another little thing we have to consider there, but we will do that in the next video. See you in the next video.